Hey guys, today I'm going to be talking about pursuit curves, which is why I have these lovely curves here. I thought that that would be a nice touch. Anyways, so this is how it applies to the unit that we were working on. So it was Unit 2, and we were talking a lot about parabolas and hyperbolas and kind of that shape of curve. So a pursuit curve is just kind of one place in nature that this kind of curve shows up, and you've probably been a part of a pursuit curve, even if you didn't realize that that's what was going on, because they're actually really common. The definition of a pursuit curve is just the curve or the path that a body follows as it pursues another body. This is why it's called a pursuit curve, because it's literally the path that something follows as it pursues something else. So some examples of this would be like a predator chasing prey. So, that could be a fox chasing a rabbit, or, a hawk chasing down whatever it is a hawk eats in the sky. Or it could be something like a homing missile tracking its target, where, if you imagine you have a plane that's headed in this direction, and then you got your missile that's over here, and your plane that's right here. Your missile's gonna head toward it, but then the plane's gonna move, and so it's just kind of this path, this curved path that the missile is going to follow. There are quite a few assumptions that we make, especially in the lower level, kind of easier way of thinking about these pursuit curves. There are quite a few assumptions that we make. The first one is that everything's moving at a constant speed, so we have no acceleration. In the case of animals and stuff like that, we're not going to factor in fatigue for now. There's obviously some other ways to do that, but for now I'm kind of at a low level. I don't know, maybe you're more advanced than I am, but we're not going to really take those things into account. Also, we have infinite agility and zero reaction time. So that means we see something, we see the thing we're chasing move, we can immediately react to it, and it doesn't matter how it's moved, we can always move to position ourselves to continue chasing it. And then mathematically, we need to know the path that the pursuant, so the thing that we're pursuing, we need to know what the function looks like. We need to know its path. So mathematically, this is what that looks like. And so it's kind of, for me, it was really hard to think about what this meant. But I liked the visuals that kind of went alongside with this, so I gave credit to where I got these visuals over there. So if you wanted to learn a little bit more about this, you can check out that link, and this is just a part of that, but it's from a lecture that this Professor Dagan did. But yeah, so we see over here kind of the image that I was attempting to draw, where this right here, the black circle on the black line, might be an airplane following its path, and then this orange guy over here on the red line would be kind of the missile, and you can see at the point where they intersect. And actually, you know, yeah, so anyways, and so we see over here, we're getting a little bit more familiar now with differentials and stuff like that in the unit that we're on. So we know that dx dt just means a little change in x, so in the x direction, over time, right? So that's what, it's just a little change in distance. And so here, doing the reading, k is kind of a scalar for the speed that the pursuer is moving. And then this right here really was pretty hard for me to figure out what exactly that meant. So I'm going to actually come back to that in a second, because I'm gonna talk about what really helped me understand what this is trying to say. But I did want to talk about this other example we have here, which is the circular trajectory. And here we see, again, kind of the same thing, where black is the thing being pursued, and red is the thing pursuing. And what I really wanted to point out about this is that just like this shows, we're not trying to predict where the red guy, the black dot is going to be. We're not going to say, hey, in 1 second, the black dot's going to be right here, and I know I can catch up to it at that time, so why don't I just go straight there? Instead, we're saying, hey, all I know for sure is where it is right now, and so I'm going to head toward it the best I can. One way that I've heard this thought of is, if you're a fighter pilot, you want to be able to point your guns directly at your enemy. Now, in reality, obviously, we probably point our guns a little bit ahead or in the direction they're moving so that we could actually hit them. And there are kind of different names for those kinds of pursuit curves. But in the most basic form, we want to point directly at the thing that we're pursuing. And so what that's going to end up doing is we're going to say, I'm going to move directly toward him, and he's right here. And then now when he's here and I'm right here, I say again, I'm just going to move directly toward him, and then it's going to move in some direction and wind up here, and then I'm going to be here, and then I'm going to say, I'm going to move directly toward him. And so what we end up doing is creating this nice curve here until we gradually come into him. Now, like I said, I had a really hard time imagining what this meant. So even though I didn't plan on writing any code for this, I had already, in my last SDL, I made kind of a gravity simulator. And so I had this environment in which I could introduce some objects and see how they interacted with each other. So what I did is I kind of took that and jerry-rigged it so that I could use it to model these curves as well. And so it took me a while to figure this out, but if we go back, we can see that we have this bottom term, and I thought to myself, hey, that looks a lot like finding the magnitude of the velocity vector. And so that's essentially what I did. So we knew that k was speed, and so what I did was find, oh no, I'm sorry, not velocity, I meant distance. That's my bad. It looks like finding how far away the thing is from you. This is in Python, but I have self is the pursuant, so the person that's pursuing, and obj is the thing that is being pursued. And so all I'm doing here is finding the x distance, the y distance, and then finding what the total magnitude of that distance is. And then I find the magnitude of the speed that I'm moving at, because that's that k value. If I go back, that's that k value, so I need to know the speed that I'm moving. And we're assuming that's constant, so I could have stored this some other way, but I wanted to be able to show it here. So I find my speed, and then here I have the distance, and so that's what was on the bottom here, was that distance value. And for the x, so this would be, I guess, technically dx, right? And if we're looking at this equation, so that dx is just the distance that I am away from the object in the x direction, divided by the total distance, and then scaled by your speed. And so if we imagine, and then the y would just be the same thing, but with the distance that you are away from it in the y direction. So again, if I have kind of an axis here, and here's my pursuant, I'm sorry, I mixed those up earlier, but pursuant being the thing being pursued, and then the pursuer pursuing, so self would be pursuer. I apologize. Anyways, so if I have this guy over here is the guy being pursued, and then the red arrow is the path that he's following, and then the guy over here is the pursuer. We got dist x would then be this distance, and then dist y would be this distance. And what this is actually going to do is he's going to always head straight for this pursuant. So at first he's going to take a straight line that way, but then after some time t, the pursuant is going to be up here, and the pursuer is going to be like right there. And then he's going to see that and say, oh, now I need to head straight toward him. And then after some time, he'll be up here, and he'll be here. And then he'll, again, try to head straight toward him. And we will continue that. And if you kind of plot these points, then you'll start to see that this is actually a parabolic shape. And then so I'm going to now show you what that looks like in my code and what that ended up looking like. And I was actually pretty happy with the way this turned out. So here you see me just kind of introducing some objects, and they kind of go at each other, and you can see here that the speed is constant, and that right there they kind of intersect. And that's kind of the one thing that I didn't quite finish as well as maybe I would have wanted to, is how they collided. But you get the point of the pursuant curves. And so here, if I pause it, I'm too late. So here, if I pause it, you see, again, this guy has his straight line. He doesn't care what's happening. But if you went back and looked at any time, you would have noticed that it went again. That's awkward. How do I? Well, you would have noticed that the pursuer is always going directly at the pursuant. Right, and so you see that curve he's taking, and he eventually, once he gets right behind that the pursuant, once the pursuer is directly behind the pursuant, he just follows the same path that he's taking. And what's actually happening is he is it's actually an asymptote, so he's asymptotically approaching where the pursuant is, the pursuant's path. Now, in real life, obviously, eventually the cheetah is going to cut off the gazelle or whatever and take him down. But, mathematically, if we were doing a pure pursuer and pursuant curve in a straight line, then they technically would never meet. They would only approach each other asymptotically. And then, so I chose to do this in a straight line because once you started getting away from the pursuant taking a straight line, it started to get really difficult to kind of, at least for me, think about what was happening mathematically. But yeah, I appreciate you listening, and that's the end of my slideshow. So thank you very much.